To get the exact area under a curve, we need to use an infinite number of rectangles. So the only way to find an infinite number of something is to incorporate a limit. Because it's going to give us a precise area, it's not going to matter if we use the left endpoints or right endpoints. So we're typically going to use the right endpoints just so we can do the addition instead of the subtraction. All right, so here's our formal definition of the area of a plane region, which just means, a two-dimensional region bounded by a curve. All right, so let f be a continuous and non-negative function on a closed interval from a to b. The area bounded by the graph of the function, the x-axis, and the vertical lines x equals a and x equals b is given by this formula. So area is equal to the limit as n approaches infinity of the summation of, this is the height of each rectangle, and this delta x sub I is the width of each rectangle, and n is the number of rectangles, which will be approaching infinities. Okay, now the problems that we're going to be dealing with and the problems that we've been dealing with, we've had the delta x be a consistent width for each rectangle, so we can actually modify this. So I'm going to write down here that since we are using a consistent delta x, we can write this formula as area equals the limit as n approaches infinity of the summation from I equals 1 to n of, and we can write it the way that we had written earlier, delta x times f of x sub I, okay? The one typed on the page is just the more generalized in case we were going to use a different setup instead of rectangles. We could have used something along these lines if we were going to be doing inconsistent widths is what we would use the original typed formula for, and we're going to be using the shorthand version, okay? So we're going to use consistent delta x's, so we're going to do basically exactly what we did in the long problem from in class today, only we're going to see it written out like this with a limit. All right, so we're going to use the same function that we used before, so it's a little bit familiar to us. I'm going to keep that visible. All right, so here we go. So I'm just going to reiterate the information that we have. So we have f of x is 2x squared minus 3. We're looking at the closed interval from 2 to 7. And we're going to use right endpoints, but we're approaching an infinite number of rectangles. And the right endpoints means that our x sub i's are equal to the a value plus delta x times I. Okay. So first we need to know what delta x is. So delta x is equal to b minus a, so 7 minus 2 over n, but now n is approaching infinity, so it's going to stay a variable, okay? So we're going to get that the delta x is 5 divided by n, okay? So as n approaches infinity, this value will approach 0 because we're going to have 5 divided by a really large number is a really small number, okay? So now we need our x sub I, which is our a value, 2, plus our delta x, 5 over n, times I. And I don't know why I wrote the times sign. I don't need the times sign there, times I. All right, now I need to know what f of x sub I is equal to. So that's 2 parentheses squared minus 3. And in the parentheses, I need my delta x, no, not my delta x, sorry, my x sub i's. 2 plus 5 over n times I. All right, and we want to clean that up as much as possible. Actually, I'm going to go down a level first. So it's going to be 2 times, if I FOIL that out, I'm going to get 2 times 2 is 4, plus 2 times 5 over ni, plus another 2 times 5 over ni, so 10 over n and 10 over n is 20 over n, so 20 over n i's. And then squaring the 5 over n, I'm going to get 25 over n squared times I squared. and I've got the minus 3. So I'm going to distribute and combine like terms simultaneously. So 2 times 4 is 8. 8 minus 3 is 5. And then I'm going to have plus 40 over n I plus 50 over n squared I squared. All right. We are now ready to write our limit statement. So we are going to have area is equal to the limit as n approaches infinity of a summation from I equals 1 to n of delta x is 5 over n from right here, okay? It's coming from right there. And then times f of x sub I, which is 5 plus 40 over n I plus 50 over n squared I squared. Now I'm going to clean this summation up a little bit, just so algebraically it's a little bit easier. So I'm going to continue writing limit as n approaches infinity until I actually find the limit. And I haven't started applying summation formulas yet, so I'm still going to write that I have a summation to do. I'm going to clean up the inside, so 5 over n, I'm going to distribute that in. So I'm going to get 25 over n plus, let's see, that's 200 over n squared times I. And then I've got 250 over n cubed times I squared. Okay? So I want to point out here that this is a constant because there's no I in it, okay? And then I've got I to the first, and then I've got I to the second here, okay? So I'm going to use the constant formula, the I formula, and the I squared formula. The only formula you're not going to see in this example is I cubed. All right, so here we go. So now this is going to be equal to, and you know what, I'm going to shift over a little bit so I have a tiny bit more space to write. Here we go. So I'm going to say equals the limit as n approaches infinity of, I'm going to actually apply the summation formula so the summation sign will go away. So a constant is the constant times n, and then 200 over n squared is a constant. I is n times n plus 1 over 2. And then the 250 over n cubed is a constant. Constant times I squared. The I squared is n plus 1, 2n plus 1, all over 6. Now this looks absolutely atrocious. I get it. I understand. But the beautiful thing about this is we're doing the limit as n approaches infinity here. Okay, we're doing the limit as n approaches infinity. That means we can use our shortcuts. So we get to say that this is like having, because it's an infinite limit, the limit as n approaches infinity of just the leading term out of this, and the leading term out of this, and the leading terms out of this, okay? So this is going to reduce down significantly without doing a lot of algebra. Now that first one is 25n over n plus. Now looking at the next one, I've got up top 200n times n, and on the bottom I've got n squared times 2. So my leading term there is 200n squared on the top, and 2n squared on the bottom. And then over here on the right, I've got 250 n times 2n. Those all get multiplied together. And in the bottom, I just have the n cubed times 6. So the numerator is going to become 500n cubed over 6n cubed. All right, and now in this situation, we have that all of the exponents in each individual rational term are equal to each other. So the limit will just be the coefficients. So this is actually equal to, I'm doing the limit so I don't write limit anymore, 25 plus 200 over 2 is 100, plus 500 over 6 is 250 over 3, And then if you get a common denominator, you'll get 75 over 3 plus 300 over 3 plus 250 over 3 is 625 over 3. And this is square units. I don't really have enough space to write it, but it's there. All right. That is the precise area under the curve. I think that's approximately 208, a little bit over that. And if we go back and look at the answer that we had before, we can see that our approximation was pretty close. All right. Actually, if I scroll back and look real quick, our approximation was 210.5875, and this one I think comes out to 208 and a third. So we were pretty gosh darn close before, okay? So that's how you do an infinite summation to find the precise area under the curve over a particular interval using right endpoints. Again, the only way that it would change up would be if you wanted to use left endpoints, but because it's a precise area, it doesn't matter if we do the left or the right because we're getting an exact answer instead of an approximation. All right, if you have any questions, let me know. Good luck, guys.